Okay, welcome back. Let's do just continue from where we left off. Let's do another example where we analyze the graph of a function. In this case, it's this e to the 1 over x. It's defined for all x not equal to 0. You can see what I want to do. I want to do everything. I want to find the intervals of increase, decrease, the extrema, what kind are they, concavity, inflection points, everything, even asymptotes. This function has asymptotes. Like I was saying last time, you can always look at a graph of a function. Let's do it right now. I've got it ready to go here on Desmos. Here we're looking at it. I can see that it's got some horizontal asymptotes. I can see lots of features of this function. Yeah, I can see looks like it's got horizontal asymptotes. I don't know their values, but with the equations, I mean, but we need to check that out. Looks like it's got a vertical asymptote, at least in one direction. There's something interesting going on at 0 from the left. We'd have to zoom in to see. Yeah, so there's a lot of characteristics, but I want to see, using our calculus, our first and second derivatives, I want to carefully analyze, give the exact intervals of concavity, increase, decrease. Maybe there's something about the computer plot that's misleading. That part from 0 from the left is kind of suspicious looking to me. When I zoom in on it, I can't quite get a feeling for what's going on. All right, so I want to check that out. Okay, so let's do some calculus. Switch back to our whiteboard screen here. Switching. Okay, so what's the first program? Take the first and second derivatives. Let's write the function down here. Because we're going to scroll, we need some room. You can stop the video right now and take these derivatives yourself. This first one, it's a chain rule problem. Yeah, if I'm going to take the derivative of that exponential function, well, the derivative of any exponential e something is e to the something, but now I have to multiply by the derivative of that exponent. Yeah, that exponent is x to the minus 1. So its derivative is minus x to the minus 2. So I'm just going to write that as minus 1 over x squared. And if we want to simplify that a little bit, that's minus e to the 1 over x all over x squared. That's in a nice form for analyzing and differentiating. Okay. I've been getting some questions. It's a good question, like how much do I simplify an answer? Well, right now I wanted to simplify that because I want to differentiate it, and this simplified form over here is nicer to do that. I can see how the quotient rule is going to work. Okay, there's a minus sign out here. I could leave it out front. I kind of like to do that. The way I'm going to differentiate this thing is I'm just going to leave that minus sign out front. And then when I'm talking about the top and the bottom for the quotient rule, I'm looking at the part only in the brackets. Okay, so the way I like to do my quotient rule is write that denominator, and then I write the derivative of the numerator. We just did that. And then I'm going to subtract the numerator times the derivative of the denominator. And you divide all of that by the denominator squared, which is going to give us an x to the 4th down there. All right. And then we just have to clean this thing up because I need to know where, I don't just want to know the second derivative. I want to know where it's 0 and where it's not defined. So I need to clean this thing up. So what can we do? Well, first of all, I see that this x squared and that x squared cancel each other. So this first term is just minus e to the 1 over x. And let's factor a minus e to the 1 over x out of that. Yeah. I see one factor of it right here. Here's the minus sign. There's another factor of it over there. So let's pull it out. The minus sign will cancel that one. So you can check my algebra at your own pace, but I'm going to pull out that thing in the numerator. And then what would we have? We would have 1 plus 2x. And that's all divided by x to the 4th. And that looks like a nice expression for the second derivative. Those are nice, I say, because I can look at them and see where they're 0, if at all, and undefined. I can look at this fraction down here and see where it's 0 or undefined. Numerator and denominator answer those questions. Okay, so let's make f prime's sign diagram first, because we can still see it up there. So once I've got derivatives and they're in nice factored form, if you're kind of trying to keep track of steps, pause right after I say this. Once you've got the derivatives and they're in nice factored forms, then it's time to make sign diagrams. It's time to make sign diagrams. So what's a sign diagram? It's just a number line. So give yourself, that's supposed to be a horizontal line. It doesn't have to be perfectly horizontal. And then what do you mark on that number line? You mark any numbers that make the first derivative 0 or undefined. I'm going to start with the undefined part. Undefined comes from the denominator. The first derivative is not defined when x is equal to 0. In my sign diagrams, I like to draw a little like asymptote thing there to remind myself it's not defined. And then, well, what about, is f prime ever equal to 0? Well, the only way a fraction equals 0 is if its numerator does, but an exponential function is never 0. So this derivative is never equal to 0. All right, so there are no other critical values, and then you just check points. If you look at that thing, I mean, I would actually look at it like this, that the exponential function and x squared are both positive, so whenever x you plug in there, that's going to be a negative number. But you can check it with your calculator that the first derivative is always negative. We'll summarize this at the end, but that means this function is always decreasing. We sort of saw it in the picture. Yeah, nice. Okay. Now you got a sign diagram for f prime. Your next order of business is to get one for f double prime. F double prime, you can barely still just see it here. Yeah. So we need a sign diagram for it. Let's make ourselves another close as we can to horizontal number line. F double prime is also not defined at x equals 0. Yeah. This exponential factor up here in the numerator doesn't contribute to being zeros. So f double prime is equal to 0 if and only if 1 plus 2x is. And that's if and only if x is minus a half. Yeah, subtract 1 and divide by 2. So minus a half, I'm going to mark on my number line over here. X is equal to minus a half. And then I'll let you check the signs on that thing. I mean, it's this positive quotient times that function with a positive slope, linear function with positive slope, but check them. The signs will go minus, minus. In here, you'll get a positive value if you choose a number between minus 1/2 and 0. And across from 0, you'll get positive. All right, so look, they didn't just alternate. We had to check them all. Stop the video and check them. Come to my office hour and ask me if it's not clear what I'm doing there. All right, and now we're in a position to answer everything about this function. We're in a position to answer everything. We need these sign diagrams in view. Oh, the asymptotes. I didn't talk about them. We'll do it at the end, but let's summarize this right now since we've got derivatives on our mind. So f is never increasing. F is decreasing on the entire real line. In interval notation, it looks like that. For this particular interval, you can also use that notation, all real numbers. It's decreasing on the entire real line. It's never increasing. Its first derivative is always negative. All right. There are no extrema. It has no local minimums. It has no local maximums. Okay. What about where's it concave up? F. Notice F, not F prime, not F double prime. F is concave up. Well, on the interval from minus 1/2 to 0, I'm going to split it because it's not defined at 0. 0 to infinity, that's where the second derivative positive. F is concave down on the interval from negative infinity to minus 1/2. And there's an inflection point where x is minus 1/2. See, we didn't really see that in that graph. Calculus has kind of taught us something cool. We didn't really see that. I didn't when we were looking at the graph. We're going to go back and look at it again. We've answered everything except for the asymptotes. How are we going to treat those things? Well, let's talk about the horizontal ones first. So the exponential function is a continuous function. So we can carry out this limit up here in the exponent, and that exponent is going to 0. So, and then by the way, that same computation is good as x goes to minus infinity. So y equals 1 is the horizontal asymptote that we saw in that picture. Okay, good. More information. We knew there was a horizontal asymptote, but now we know where. See, that's what the calculus is doing for us. And then finally, at 0, we need to look at left and right-hand limits. Let's start from the right. So once again, it's all about what this exponent is doing. And as x goes to 0 from the right, 1 over x goes to infinity, positive infinity. Yeah. So if you want, we could write that this is say, the limit as t goes to infinity of e to the t, where I'm just substituting t equal to 1 over x. And 1 over x goes to, t goes to infinity as x goes to 0 from the right. So that limit's infinity. So that's that vertical asymptote that we saw. And if we take the limit from the left, well, it's the same thing, but now 1 over x is going to minus infinity. So if we're going to switch this variable t, as x goes to 0 from the left, 1 over x goes to minus infinity. And the limit is t goes to minus infinity of e to the t is 0. So we kind of saw that in the graph, that the graph was kind of approaching 0. Let's go back now. We're done. You can stop this and review. I hope that it was a useful example. It's kind of a fun example. Let's switch back to Desmos. And well, should we zoom out a little bit first? We know what that is now. If we put in, say, the line y equals 1 in there as a horizontal asymptote, why are you being persnickety? There you go, y equals 1, nice green horizontal asymptote. We've calculated that that's its value. X equals 0 from the right. We're going to infinity. Now it's time to zoom in. Zoom in just a touch here. So we're below 1. 1 gives us a little bit of a scale. And we said there was an inflection point. And if I turn this on, we can see it. There it is. It's very subtle. The graph is very flat there. But look, it's always decreasing. It's always decreasing. And in order to kind of approach 0 like that, it almost had to change concavity. Well, I guess that's not true. It could have come in like this. And we calculated that limit from the left. The limit from the left is 0. All right, so what I tried to do in here, in addition to give you another example of the procedure of answering all these questions with sign diagrams, is also to give you the flavor for like what we're doing. We can look at a graph in Desmos, but I didn't know that there was an inflection point at x equals minus 1/2. You know, and if you want, you can get out a calculator, or you can turn on the label. Desmos says the y value there is about 0.13. I didn't know that. I didn't know that the horizontal asymptote was y equals 1, so all the calculus is what's doing that for us. All right, I hope that's useful. Thanks for listening. Maybe we'll do another example.